Hello, everyone. This is a exam 2 review for statistics. So I'm going to be going over the four main concepts. I don't know why this is exam 1. It's literally exam 2. I don't know. I think this class makes me lose my mind. Anyways, for exam 2, there are four main concepts: probability, distributions, confidence intervals, and hypothesis testing. And these coincide with the orders of the chapters that we went over and the concepts. So first is probability. Probability is the outcomes that occur over the total number of outcomes. And the sample space is the set of all possible outcomes. So for example, if we flip a coin, the sample space is just heads or tails. Whereas if we flip two coins, then we could get heads, heads, tails, tails, heads, tails, and tails, heads. So there are four possible outcomes to this to the second power. And the probability of an event occurring is between 0 and 1. It can be 0, which means it's impossible. And if the probability is 1, that means it has a 100% chance of occurring, meaning that it always occurs. An example of probability is if you flip 3 coins, what's the probability of getting at least 2 tails? So first you write out the sample space, you write out heads, 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 tails, and so on. And then you find the ones that have at least 2 tails, meaning 2 or 3 tails, and I've circled them here. Then we can write the sample space. We have the sample space, so we can write the set, which I just call A, which is the probability of getting at least 2 tails. And then so we have 4 outcomes where you have at least 2 tails over the total number of outcomes, which is 8. So 4 over 8 is 1/2. So you have a 50% chance of getting at least 2 tails. Next is the intersection and the union. So if we want to talk about the probability of getting A and B, or the probability of getting A or B, for this example, I have a sample space of 1, 2, 3, 4, 5, and 6. And then I have sets A and B. So what is the probability of having A and B occur? This is called the intersection, which is an upside down U. So this is going to be the commonalities, the shared values of A and B. And so if you compare the sets A and B, you see that they both have a 3 and a 4. So that would be the set for A and B. So the probability of that is 2 out of 6, because we have 6 different numbers in the sample space. So you have a 33% chance of this occurring. Next is the union, A or B, and it has a regular U, so you can remember that it's the union. So here it's just the set of values that are either in A or B, and we can go back and see. So it would just be all of the numbers here. We don't repeat the numbers. So it would be 1, 2, 3, 4, and 5. And so the probability of this happening is 5 over 6, 83.3%. Now the complement of a set is all of the values that are not in that set. And we can denote this with a little C exponent. And to find this probability, we just do 1 minus the probability of A, for example. So if we want to find what is A complement, so that would be the values in the sample space that are not in A, meaning 5 and 6. And to find the probability of A complement, it is 1 minus the probability of getting A, so 1 minus 2/3. So the probability of getting the complement of A is 1/3. Next, we have the probability of getting A given B. Again, using a similar example. The formula is the probability of getting A and B divided by the probability of B. And we found the probability of A and B to be 1/3 or 2/6. And then the probability of getting B is 3/6. So 2/6 divided by 3/6 is 2/3. So the probability of getting A given B is 2/3. Here's a more complicated example. So 500 students are at a school. 150 are enrolled in algebra, 80 are enrolled in chemistry, and 30 are enrolled in algebra and chemistry. And at the top left or top right, you can see that I've drawn a picture that can be very helpful. So what is the probability that a student is taking algebra? So this is the probability of getting A. So it would be 150 divided by 500, which is 3/10 or 30%, because we have 150 enrolled in algebra out of 500 total students at the school. What is the probability that a student is taking chemistry given that they are taking algebra? So this is the probability of C given A, which is the probability of a student taking both chemistry and algebra divided by the probability of a student taking algebra. And again, we're actually given this in the problem. So it would be 30 divided by 500, and then that divided by 150 divided by 500, which equals 30 over 150, which equals 1/5 or 20%. And next, what is the probability that a student is taking algebra given that they are taking chemistry? So this is just where you flip the probabilities. So it's again the probability of a student taking chemistry and algebra divided by the probability of a student taking chemistry. So we have 30 over 500, all divided by 80 over 500, which is 3/8. Next, we talk about the difference between independent and dependent events. Two events are independent if the occurrence of one does not affect the probability of the other. So for example, if we want the probability of E given F, and these events are independent, so that probability would just be the probability of E, because the probability of E does not depend on the probability of F occurring. And we can derive some rules for this, and a lot of times, especially on the homework, you were given certain probabilities, and using those probabilities, you have to find other probabilities. So one way you can do that is using these equations and rearranging them. The multiplication rule is if you, for this is for independent events. If you want to find the probability of E and F, it is the probability of E times the probability of F. And for dependent events, it is the probability of E given F times the probability of F. The addition rule for the probability of getting A or B is the probability of A plus the probability of B minus the probability of A and B. And for mutually exclusive events which don't occur together, the probability of getting A and B is 0. So the probability of getting A or B is just the probability of A plus the probability of B. And finally, What is the probability of getting heads twice after flipping a coin? So this would be the probability that you get heads on the first flip times the probability of getting heads on the second flip. So the probability of getting heads in both cases is 1/2. So you would just multiply 1/2 times 1/2 and you get 25%. Next, we briefly touched on combinations of n distinct objects taken r at a time, otherwise known as n choose r, and I've had this formula here. To give you an example, if we have a class of 20, how many pairs of students can be made? This is 20 choose r, so you have 20 factorial over 2 factorial times 10 minus 2 factorial. And an easy way to calculate this is writing the 20 factorial on the top out until you get, it should be 20 times 19 times 18 factorial. Then you can have the 18 factorials cancel. So then you just have 20 times 19 over 2 factorial, which equals 190. So 190 pairs in a class of 20 can be made. Next are distributions. There are a few kinds of distributions, and you definitely need to understand those because they're critical for confidence intervals and hypothesis testing. Some basic concepts at the beginning. A random variable is a numerical measure of an outcome denoted with capital letters like capital X. And a discrete random variable has countable possible values. And these probabilities, again, have to be between 0 and 1, although they can be 0 or 1. The mean of capital X, also called the expected value, is the sum of the possible values times their probabilities. And the standard deviation of the discrete random variable X is the value minus the expected value squared times the probability, all summed together, and then you take the square root. And if you want the variance, you just square that. Binomial distribution has a fixed number of independent trials. It deals with the concept of success or failure, although oftentimes it won't exactly mean success or failure. You'll have to think about it. Usually it's with something either occurs or it doesn't. And the probability of success of something occurring is fixed for each of the trials. So for each event occurring, the formula is n choose x times the probability to the little x power times 1 minus the probability to the n minus x power. But more often than not, you will probably encounter the specific distribution or the approximation, which we'll get to next. So the binomial distribution of big X has a mean of n times p, the expected value, and a standard deviation of the square root of np times 1 minus p. And the binomial distribution is simple enough to understand, but if you have a large sample size, you would be better off approximating it, which I think I have down here. Yeah, so approximating binomial distribution because the sample size is too large and I'm too lazy to compute the probability. So two conditions have to be met. N times p has to be greater than or equal to 10, and then n times 1 minus p has to be also greater than or equal to 10. Then you can say x is approximately normally distributed with a mean of n times p and a standard deviation of the square root of np times 1 minus p. And I do see you, Meg. If you have questions, you can unmute or say something in the chat. Otherwise, you can follow along. I'm going to be going through the entire exam review.
Okay, I'm just chilling. You're good.
Okay, yeah, no problem. And yeah, this is going to be recorded. So one example that we had to approximate the binomial distribution, and actually a good example of why approximating binomial distribution is a lot better than having to do it, is number 5 on the practice exam. So we had a sample size of 200, which is pretty large. And you can see that our conditions for approximating it were met. NP was greater than 10, and n times 1 minus p was also greater than 10. The probability for that question was 0.59. So we can just plug those numbers in since we have our conditions met for approximating it. So the mean is 118 and the standard deviation is the square root of 48.38. And the question wanted the probability that x is greater than or equal to 135. So first you need to draw a picture. Again, the mean is 118, so it's right smack in the middle of our normal curve. And then we're looking for the probability that it's greater than or equal to 135. So I've shaded it on the graph. You find the z-score by doing 135 minus 118 divided by the square root of 48.38, and you get a z-score of 2.44. Keep in mind for a lot of these z-score calculations, you can round and you'll get very close to the same answer as if you did not round. It's more important that you just show your work and that you're consistent in rounding or not rounding. So you go to the z table and you look for 2.44 and you find the decimal corresponding to a probability of 0.99266. But we're looking for the probability of x being greater than 135. So we actually have to subtract the 0.99 from 1. So then we would get a probability of x being greater than or equal to 135 being 0.734%. Now, if we had done this with regular binomial distribution, we would have had to do the probability that x equals 135 plus the probability that x equals 136, and we would have had to add all of those up until we got to 200. And again, if you go back to the distribution, we would have to do n choose x, et cetera, a bunch of times, and that's just too much work. So if we have these conditions met, then we can just approximate it and it's a lot easier. So the next distribution is the sample mean, x bar. If the sample size is large or if the problem says that it's normally distributed, then x bar, the sample mean, is normally distributed with a mean of the population mean, mu, and a standard deviation of the population standard deviation, sigma, divided by the square root of n, the sample size. I think I might have an example here somewhere. Yes. In the sleep study, daily sleep among students was approximately normally distributed with a mean of 7.13 hours and standard deviation 1.67 hours. You take a sample of 60 students and want to know the probability that the average amount of sleep is less than 6.9 hours. So it's important to write down what you know first. That will help you figure out what distribution you are going to need to use. So we were given a mu, a population mean of 7.13, a sigma, a population standard deviation of 1.67, and a sample size of 60. So we're going to be using the distribution of the sample mean because we're taking a simple random sample and we're looking for a probability. So in this case, we're looking for the probability that the sample mean, the average amount of sleep is less than 6.9 hours. So going back to the distribution of the sample mean, the sample mean is just the population mean, mu, 7.13, and the sample standard deviation is the population standard deviation 1.67 divided by the square root of the sample size, radical 60. And if you do that, you get a sample standard deviation of 0.22. Next, we should draw a picture to figure out what we're looking for. So first you need to put the mean of the distribution. So that's 7.13. And we're looking for the probability of getting the average amount of sleep being less than 6.9 hours. So I've shaded that there. And then we can find the z-score to find the probability. So it's 6.9 minus our mean, 7.13, divided by the standard deviation, 0.22. This corresponds to a z-score of negative 1.05. And since we're looking for the probability to the left of 6.9, we don't need to subtract the probability from 1. And if you go and look for negative 1.05 on the z-score table, you'll find that this corresponds to a probability of 0.15. Going back to why I said that the binomial distribution is kind of painful to calculate. This is a relatively short example, but even then, there's a lot of calculations, so there's a lot of room for error. But I thought I would throw it in here anyway, just in case you see it on the exam. So it says a basketball player makes 85% of free throws. Last game, they missed 4 out of 7 free throws. What is the probability that they miss 4 or more free throws next game? So we're looking for the probability of missing 4 or more free throws. But to make things easier, we can calculate the probability of the complement and subtract this from 1. So we can do 1 minus the probability of missing 3 or less free throws. And if we do not approximate the binomial distribution.
Did you subtract to find the x is less than 3? Because like if you left it as greater than 4, like you would then have to calculate every probability after that. So you did that to like limit so that you only have to calculate 0, 1, 2, 3. You know what I mean?
Yeah.
Or why does that matter that you switched it?
I guess it doesn't really matter. It's just preference on what makes it easier. And again, this is from the formula that we discussed in probability. So if we go back to The complements. Where are the complements? And I end up missing the complement somewhere. I think I skipped over it. Do I not have it here? I swear I must have it here. Complement.
Or like, did
complement.
you just do
Here
that
it
to
is.
make it easier to start from 0, 1, 2, 3?
Yeah, it just makes it easier. So yeah,
Okay.
for the complement, we can just do 1 minus the probability of basically the other side. And we know that we can do this from the, where did I put it? It's here somewhere. Anyways, it might be more clear once we go back to the problem.
Okay.
So we're trying to find the probability that they miss 4 more free throws. So that's the probability that X is greater than or equal to 4. And this actually comes from your homework. And yeah, you could calculate the probability of just X is greater than or equal to 4. So that would just be, well, the problem is that you don't know how many total free throws they're going to make. So, but you do know, like, they're going to make, you know, like you could have 0 free throws, 1 free throw, 2 free throws, 3 free throws. But the thing is, like, we're taking a look at past data. So in a past game, we know that they had 7 free throws total, and they happened to miss 4. But on this next game, we have no clue the number of free throws that they're going to have. They could have like 5 free throws and miss 1 of them. So that's why we're not doing it to where we were saying just the probability of X greater than or equal to 4, because that could go on and on forever. We have no clue how many total free throws they're going to do.
Okay,
But
yeah, right.
yeah,
Okay, thanks.
yeah, these ones are kind of confusing. It's just, it's a lot of things not being explained, especially in the book, especially in the homework.
It's like,
So
I feel like my biggest problem is that I don't know where to start. Like, I wouldn't know to do that if I saw this question on a test, you know what I mean? That's why I would just wanted you to explain it.
yeah, that's the problem with this exam, is going to be a lot of reading the problem and trying to figure out what it's asking for, because it's a lot of interpretation of the question, and if you interpret it wrong, then the entire thing's going to be wrong. So I think that's going to be a problem. But yeah, you know, they only give you so much information, so you only have so much to work with. So if you can write that out, like what exactly do they give you for each problem, that might be helpful.
Okay, thank you.
So yeah, since we don't set a limit to the number of free throws, we're going to take the probability of X being less than or equal to 3, and we're going to subtract that from 1, which that's the complement for this problem. So it would just be, we're going to take the probability of having them miss exactly 0 free throws, 1 free throw, 2 free throws, and 3 free throws. We're going to add those probabilities together, and we're going to subtract them from 1. And again, so we're going to use this formula, n choose X times the probability to the little x power times 1 minus p to the n minus x power. So this formula, I feel like, is a lot clearer once you actually start plugging numbers into it. So the total number of free throws that we know we have to work with is 7. So that's our n. And so for the probability that they miss 0 free throws, it's going to be 7 choose 0. And if you don't remember the combinations formula, go back up in the PDF of this review. So you're going to calculate that, and it's going to be times the probability of missing a free throw, which they don't actually give you, but they give you the probability of them making the free throw. So if they make 85% of the free throws, then they miss 15% of the free throws, or 0.15. So that's going to be to the 0th power, because we're looking for the probability that they miss 0 free throws, times 1 minus 0.15. This is the probability that they make free throws, again, 85%, and this has the power 7, the total number of free throws, minus 0. And if you do all those calculations, you'll get 0.32058. And similarly, for all of the other probabilities, you're going to do the same thing. So take a moment and just look at these and see how the numbers are put into the formula. So once you get all of those numbers, you're going to add those together and subtract them from 1. And you find a probability of 0.0121. And this is so confusing, and this is why binomial distribution sucks, and why approximating it is a lot better. But because it's kind of a small scale, we have a small sample size of just 7 free throws, then yeah, I mean, you can do it this way, but it just is not very fun. And when we had the sample size of 200, imagine doing this for the probabilities of getting like 135 all the way to 200. That's like way too much. So it's a good thing that if you can approximate binomial distribution, that you should definitely do that. But you have to make sure that those 2 conditions are met, that they're greater than or equal to 10. Otherwise, you cannot approximate it, which is why we can't really approximate it here. The last distribution is the sample proportion. And again, we have 2 conditions. So NP has to be greater than or equal to 10, and N times 1 minus P also has to be greater than or equal to 10. And if this is the case, then P hat, which estimates the true proportion P, is normally distributed with a mean of P and a standard deviation of the square root of P times 1 minus P divided by N. Our example here is that 15% of the 1,750 biology students at a university say they have experienced extreme stress levels, which you might also be experiencing now, but I don't blame you because I am too, in the past month. You don't know this proportion, so you take a simple random sample of 160 biology students and you find 10% say they have experienced extreme stress levels in the past month. That seems pretty low to me. If the true proportion is 15%, what is the probability that more than 10% of the sample would say they have experienced stress? So because it's talking about proportions, that should clue you in on that it's you have to use the distribution of the sample proportion. So before you can do that, you need to check that the 2 conditions are met. And because we have a large sample size, you can kind of estimate it in your head that they're going to be met. But I've plugged in the numbers. So NP is 160 times 0.15, that's 24. So that's definitely greater than 10. And then n times 1 minus p is 160 times 0.85, which again is greater than 10 because it's 136. So we're looking for the probability that p hat is greater than 0.10. So from these conditions, we know that p hat is normally distributed with a mean of the proportion, which we're given it's 0.15, 15%. And then it has a standard deviation of p times 1 minus p, so 0.15 times 0.85 divided by n, which is, where did I put it? 160. And then we do that and take a square root and you get 0.028. Next, we draw our picture. So you draw the mean in the middle, which is 0.15, and you draw the probability that we're looking for. So we're looking for something with 0.10. Specifically, we're looking for the probability of p hat being greater than 0.10. So I've shaded the appropriate area of the curve that we're looking for. Next, we do our z-score. So it's just p hat minus the mean divided by standard deviation, which we have found using the distribution. So if you do that, you get negative 1.78 as the z-score. You go look for that in the table. You should get a probability of 0.03754. And now remember, the z-score finds the probability to the left of whatever value you're looking at. So if you want something greater than that specific probability, you need to subtract the probability that you get in the from the z-score from 1. So you do 1 minus 0.03754, and you get a probability of 96.327%. The third topic is confidence intervals. The basic formula for confidence intervals is the estimate plus or minus the margin of error. And I've drawn an example. Well, it's not really an example because this is something that's kind of impossible to see in real life. But just a picture that comes from the book that might help you understand what's going on more. So we say that for a chosen C% confidence interval, C% of constructed intervals will contain the true value of the parameter, and then 1 minus C% will not contain the value. So when we are constructing confidence intervals, we're trying to capture the true value of the parameter that we're estimating, because these distributions, X bar and P hat, are they're estimating the true value of the population. But the problem is, yeah, we can take a simple random sample easily enough of 100 or 1,000 or even 10,000 or more people or objects, but it's very difficult to take a sample that is the size of the population. The population could be in the millions if we want to know something about a city. So instead, we have to use these distributions to estimate it. And we want to know if we're going to be able to capture the true value of that population. So in the picture, I have driven, I have drawn a normal curve. And here I'm looking for the population mean, mu. So I'm taking samples and I'm calculating the sample mean, X bar, and using that I can calculate the confidence interval, which I've drawn below the curve. So what this is showing you is that some of the confidence intervals I drew, if you draw a dotted line down from mu all the way through the confidence intervals, you'll see that the dotted line hits some of the confidence intervals and misses others, which means that they either contain the true value of mu, or they do not contain the true value of mu. And if we had a 95% confidence interval, if we constructed 100 confidence intervals, 95 of them would contain the true value of mu, and 5 of the confidence intervals would miss the true value of mu. And increasing the confidence level, for example, going from 95% to 99%, widens the intervals because we're more likely to capture the true value of whatever parameter we're looking for. Here's more formulas, because statistics is all about formulas just as much as it is about interpreting the results of plugging stuff into these formulas. So if we want to try and capture the true value of a population mean, mu, and we are given the population standard deviation, sigma, then we have this equation here that we can use. So it's the sample mean x bar plus or minus z star, which I'll get to in a minute, times sigma divided by the square root of n. And the curve on the right shows us what z star means. So the value in the middle is the confidence interval, and then on either sides, that's how we're going to get our margin of error. So on either side, the probability is just 1 minus c divided by 2. So for example, if we wanted a 95% confidence interval, it would be 1 minus 0.95 divided by 2. And then from that, we can take that probability and look for it to find the z-score. I think I have an example somewhere. Maybe I don't have an example of that one. But most of the time you won't really know sigma, again, because it's very hard to collect population parameters. So more likely sigma will not be known. So you'll have to do the t-score. So it's essentially the same. You have to keep in mind the degrees of freedom, df, on a t table instead of a z table. Instead of z, you're using t, and instead of using sigma, you are using the sample standard deviation s. And you have to make sure that the sample was formulated randomly, that it's normally distributed. So either the sample space has to be greater than or equal to 30, or it'll say the original distribution was normal or roughly symmetric. And I believe I do have an example. Yes, McDonald's wants to estimate the average caloric content of a new burger. They take a simple random sample of 14 burgers and find the sample mean is 700 calories with a sample standard deviation of 50 calories. Construct a 95% confidence interval for the mean caloric content. Now you'll notice they give you the sample standard deviation, but they don't give you the population standard deviation sigma. So this should clue you in that you need to use the t-testing instead of the regular confidence interval construction using the z-score. So again, we have our basic confidence interval formula, x bar plus or minus t star times s divided by radical n. In this case, our x bar, our sample mean is 700. Our sample standard deviation is 50. We have a sample size of 14. we can find the degrees of freedom, which is just n minus 1, so 14 minus 1, which equals 13. This is important for finding t on the t-table. And so on the t-table, I might actually be able to look it up so I can show you what I'm talking about. Because if you can't read a t or a z table, it's time to learn. So we said, no, go away. We said that we are looking for a 95% confidence level. We had 13 degrees of freedom. So first, find the degrees of freedom on the left column. So we go down to 13. And then, so you can either read it from the top or from the bottom. I think it's easier to read it from the bottom since we know it's 95%. So we go 13 degrees of freedom, 95% should get you 2.160. That is our t. So you come back and you can plug that in. And again, so we know S and we know N. So it's just a matter of plugging these values in. So we're going to get 700 plus or minus 28.9. So we have a confidence interval from 671.1 to 728.9. Do we know that the value of the value of mu is within those values? No, we don't know. But if we were to construct more confidence intervals, we could say that 95% of the total number of confidence intervals would contain the true value of mu. You can also construct confidence intervals about a population proportion. Again, you need to check that NP times 1 minus p is greater than or equal to 10. A reminder, p hat is just the occurrences, the events divided by the sample size. And this should be relatively familiar since we've been talking about distributions, but we can't use just p this time because we are trying to estimate p. So instead, we're going to do p hat plus or minus z star times the square root of p hat times 1 minus p hat divided by n. And I have an example below. It says a school has 6,250 students. 250 students were selected randomly and asked if they liked the cafeteria food. 142 said yes, which also sounds like way too high. Calculate a 99% confidence interval for the proportion of all students who liked the food. So we don't really have the time or the resources to survey all 6,250 students. So a more reasonable sample size would be 250. And from that data we collect from the 250 students, we're wanting to make some inferences about what the rest of the students might think. And to do this, we can calculate a 99% confidence interval to try and estimate the true percentage of that 6,250 students who might like the food. So first, we can find our p hat, our sample proportion. So in our sample, 152 students said yes, they liked the food out of 250. So our p hat is 0.568. So next we can draw a picture of our normal curve, and remember to verify those conditions were met. Since we have a large sample size of 250, that's definitely good enough, so we can use the proportion distribution. So we have 99% in the middle. of our normal curve, since we are using a 99% confidence interval. And on either side of that, that is 0.005%. So I always take the minus z star, because that will give you the true value for the z table, but you can also do plus z star, but then you have to add the probability. So I just think it's easier to do the one on the left. So what you're going to do is you're going to look for 0.005 on the z table. And I can also pull up the z table. Okay, so we're looking for, this might be kind of small. Maybe I can. Okay, so again, I really don't care. So I'm looking for a negative z star. So it's going to be on the negative z table, and I'm looking for a probability of 0.005%, which is going to be in the middle. So 0.005%. So I could sit here for a while and look for it, but I've already found it. And it should be negative 2.575. Now, do note that the z table only goes to the hundredths place. So sometimes in the z table, you'll find that you have two numbers that you're in between when you're looking for the 0.005. They're not quite 0.005. So you can take the average of those z-scores. That's what I've done. So you just plug all the numbers in. So our p-hat is 0.568, and then we do plus or minus that z-score, minus 2.575, and then we're multiplying it by the square root of 0.568 times 1 minus 0.568 divided by 250. And once you do that, you get 0.568 plus or minus negative 0.08. So the confidence interval we constructed is between 0.488 and 0.468. Again, we don't know that that interval contains the true population proportion, but if we constructed more confidence intervals, we could say that we're 99% confident that, you know, if we make 100, 99% or 99 of them will contain the true population proportion, and then one of them will not. Lastly, to combine everything that we've learned, we talked about hypothesis testing. In hypothesis testing, we first have to write two hypotheses. First is denoted H0, the null hypothesis, which is the status quo. The second is H sub 1 or HA, the alternative hypothesis, which is our statement to be tested. And we have different ways that we can write the null and the alternative hypotheses. So a two-tailed test is when we wanted to check that, for example, mu is not equal to something. A left-tailed test is when we want to see if mu is less than a value. And a right-tailed test is if we want to see whether mu is greater than a value. And keep in mind that for the null hypothesis, in class and in the examples we have gone over, we always have it being equal to a value. And we have type 1 and type 2 errors, as we've discussed. The type 1 error is also related to the level of significance, alpha, Alpha is the probability of getting a type 1 error. And if we want to find the p-value, the probability of getting the event of the alternative hypothesis, given that the null hypothesis is true, we want to compare it to alpha, to the level of significance. And if it's not specifically stated in the problem, we treat it as being 0.05. So if p is small, less than alpha, at a default of where alpha is 0.05, then we reject the null. And we can say that we have significant evidence for whatever the alternative hypothesis is. So we either reject the null or we say we do not reject the null. We don't say that we accept it. And the question that hypothesis testing is trying to get an answer for is, what is the probability of getting our sample results if we assume the null hypothesis is true? So if we assume that the status quo is true, what are the chances of getting our results, which is different than the status quo? And a general example here for proportion is we state our null hypothesis, p is equal to x, and our alternative is that our proportion is greater than x. We're taking a simple random sample, so we're using p hat. We find the p-value using the z-score, and then from the z-score we find the probability, and if this probability is less than alpha, we can reject the null hypothesis. One confusing occurrence is with a two-tailed test. So that's on either side of our probability in the middle of the normal curve. So we have to take twice the probability that z is less than whatever our statistic is minus the parameter divided by the standard deviation. This is essentially saying that we're taking twice the probability that corresponds with the negative z-score. Here's an example. During the holidays, the average amount of money customers spend in all stores of a specific chain is 168. A manager in a town believes that this is different, so she takes a simple random sample of 36 customers and finds the mean to be 169.5 with a standard deviation of 3.9. At a 95% confidence level, can you reject the null? So first, we have to write our null hypothesis and our alternative hypothesis. And it's important to interpret what the question is asking for. What is the goal and what are we trying to look at? So we know that the null hypothesis, the status quo, is that the average amount of money customers spend in all of the stores of a chain is 168. So we say that mu is equal to 168. But the manager believes that this is different, that it's not 168. So the alternative hypothesis is that mu is not equal to 168. So we've stated our hypotheses, and now we should write down what we know from the problem, what we're given. So the simple random sample had a sample size of 36, and it had a sample mean of 169.5 with a sample standard deviation of 3.9. Our confidence level is 95%. So our alpha, our level of significance is 1 minus 0.95, so it's 0.05. Again, if the problem doesn't specifically say at 95 confidence, or if it doesn't give you an alpha, this is the value that you can assume. So next, we can calculate a z-score. We do not know what sigma is, what the population standard deviation is, but we were given the sample standard deviation. So we can just use that to replace sigma. So we can plug in the numbers and we get a z-score of 2.31. And I recommend actually doing the negative z-score. So negative 2.31 in the z-score table. You'll find that this corresponds to a probability of 0.0144, but because we are looking for a probability of the population mean not being 168, then we're looking for it being lower and higher. So we actually need to double that probability to get a p-value of 0.02088. Then we compare this to our alpha and we can see it's less than 0.05, so we can reject the null, and we can state that with a 95% confidence level, we have significant evidence to believe that the average amount shoppers spend is not 168. Do you have a question?
No, I'm good. I'm just listening.
Okay, this is my last example. So this example is if a question for hypothesis testing is asking about proportions. It's very similar. All of these are essentially similar. The most important thing is that you got to remember the distributions. Otherwise, you won't get the right formula. So this gives us a level of significance in alpha of 0.05. We were given a sample size of 200 and a p-hat of 0.11. So in our hypotheses were that the population proportion is 0.08, and the alternative is that the population proportion is not 0.08. So remember, you always got to verify that those conditions are met. But since we have a large sample size, you can kind of skip it. If the sample size is sort of low, then it's good to check. But in this case, we know that the conditions are met, so we can just find the z-score, and we get a z-score of 1.56, which corresponds to a probability of 0.94062. And this is actually the other way. We did not find the negative z-score, so this is a valid way of doing it as well. But just remember, you have to actually subtract that from 1. So you can either, in the example above, you can either find the probability to the left of the negative z-score, or you can find the probability of the positive z-score, which that probability is on the right, and then you have to subtract that from 1. Either way, you get the same answer. Because this is a two-tailed test, since we're testing to see if the evidence for whether p is not 0.08, you have to double the probability. So that's why I'm multiplying the p-value by 2. And if you do that, you get a p-value of 0.11876. And this is greater than our level of significance, so we do not reject the null, and we say something like, we do not have significant evidence to reject the null. Always go back and read the problem to see what it's specifically asking for. It's better if you cater your answer to the specific problem and what the researcher or the tester is trying to look at. So that's the end of the review, and please ask me any questions that you might have. Review the notes from the book, from the lectures, from practice problems, and good luck on the exam.